Hey guys, welcome to our next lesson. This is a new unit, gas laws. This unit has a couple different parts to it. We're going to cover gas laws over the next 2 weeks. And we're going to start with something called KMT and then a brief lesson about conversions. So KMT stands for kinetic molecular theory. It's really just 5 ideas about the way gases behave that allow us to mathematically calculate a relationship between a couple different variables. So we'll just go through these quickly, and I'll break down kind of in English terms what some of these theories mean. So the first one says a gas consists of small particles traveling in straight line motion. All that means is, we kind of know this already, that gas molecules are tiny, and well, just all molecules are tiny, but they're small and they move in a straight line until they bump into something else, whether that's the walls of the container or a different gas molecule. They don't go in like zigzaggy, curvy paths, and they don't just change direction without something to cause that. The second part says molecules of gas occupy zero volume. Now what this means is that the gas molecule itself is so ridiculously small compared to the container that it's in that we essentially call the volume of the gas molecule zero. Another way to kind of look at that is that in a gas, the space in between the gas molecules is basically empty space, like there's nothing there. So the volume of a gas is mostly empty space. The third line here says collisions between gas molecules have zero energy transfer. What that means is that when a gas molecule bumps into a different gas molecule, those two molecules are going to change directions, and they're going to change directions with the same amount of energy that they collided with. So if you think about, like, if you hold a basketball up and you just drop it to the floor, it's going to bounce, but it's not going to return back to its original position. That's because some of the energy, some of the kinetic energy that basketball had in falling to the floor is transferred to the floor itself. And so when it starts its return path back to its original position, it doesn't have enough energy to get there. The kinetic molecular theory says that gas molecules don't do that. They maintain all of their kinetic energy even after they collide with something. The fourth part of the kinetic molecular theory is that there are no attractive or repulsive forces between gas molecules. So if you think about these gas molecules bumping into one another, we know that atoms contain protons, neutrons, and electrons. 2 of those subatomic particles have charge. Protons are positive and electrons are negative. And if I have 2 molecules of gas that collide with each other, logically it makes sense that there should be some sort of attraction or repulsion because they both have protons and electrons. So like their protons should repel each other, and one molecule's protons should have some attraction to the other molecule's electrons, even if it's just in the tiniest amount. But the kinetic molecular theory really simplifies the idea that when gases collide, there's no attractive or repulsive forces, that we're kind of ignoring the fact that gas molecules could potentially have some sort of attraction or repulsion to each other. And part of the reason for that is, hopefully you already know that gas molecules are moving really, really, really fast. And since they are moving really, really, really fast, the collision between 2 molecules occurs so quickly with such great force that any attractive or repulsive force that might have been present is basically overcome by the fact that those 2 molecules slammed into each other so quickly. And then the last part, line 5 there, says the average kinetic energy of gas molecules is directly proportional to temperature. So if you recall, back in the thermo unit, we talked about how temperature really just measures kinetic energy of molecules. So if molecules are moving fast, the temperature is high. If molecules are moving slow, the temperature is low. And that's all this says. The average kinetic energy, the speed at which the molecules are moving, is directly proportional, meaning if one goes up, the other goes up to the temperature. So if we measure the temperature as being high, that means the molecules are moving quickly. If we measure the temperature as being low, the molecules are moving slow. So just a quick reminder, hopefully you guys remember that there are different scales of temperature conversions. And in doing some of the math calculations in this unit, it's really important that you know how to convert between Celsius and Kelvin. I included the Fahrenheit temperature conversion here on these notes, although we're not going to ask you to do that. So if you have a temperature that's in Celsius and you want to convert it to Kelvin, you just simply add 273 to the Celsius number. If you want to go the other direction and you have a temperature in Kelvin and you want to convert it to Celsius, you subtract 273. Sometimes I find it difficult to remember which way is which, and so I just remind myself that there is no temperature lower than 0 Kelvin. So if I'm trying to go to Kelvin from Celsius, I'm going to add 273, because if I subtracted 273, that could potentially give me a negative Kelvin, and that's not possible. It is possible to have negative degrees Celsius. This is going to be important when we do the math, like I said, because our temperatures, when we start plugging them into these equations, need to be in Kelvin temperature, because when we're manipulating some of our variables, we need to make sure we're working with all positive numbers. So we don't want to use any Celsius, because that could potentially give us a negative value, and we don't want that. And also, when you're working on your UT Quest, be very careful about where it says answer in units of. If it tells you to answer in units of Celsius, make sure you convert back to Celsius. You still have to do the math in Kelvin, but you can convert the temperature back to Celsius. If it says to answer in units of Kelvin, then you can just leave it in Kelvin. So 2 quick examples. Convert 35 degrees Celsius to Kelvin. Easy enough. We just add 273 to get 308 Kelvin. And notice that for the unit, Celsius has a degree symbol, but Kelvin does not. And that is standard for reporting the unit. And then the last one, convert 197 Kelvin to Celsius, degrees Celsius. We'll just subtract 273, and there's a great example of how Celsius can be negative, but Kelvin can't. So we get negative 76 degrees Celsius. So we also need to talk about pressure. Pressure is another thing that we look at when we're talking about gases. Pressure comes from the amount of force exerted on a specific area. So if you think about, say like you have a canister, like think of, hairspray or a can of spray paint or something like that. And there's gas molecules inside of that. And those gas molecules are moving really, really quick. Well, every time those gas molecules strike the walls of the inside of the container, that's how pressure occurs. So it's every time a gas molecule hits the walls of its container on a specific area, that's where we get pressure. In the extension activities, there is an Ellen DeGeneres video that kind of shows you an example of pressure in a fun way. So feel free to click on that and watch that. But there are also different units of pressure, and you have to be able to convert between them. So one unit is this very first one, ATM, that's short for atmospheres. And then there's another unit, mmHg, which stands for millimeters mercury. Torr is another unit of pressure. kPa stands for kilopascals. And then PSI is pounds per square inch. So each of these things are equivalent to each other. So if you have a unit in, like say you're given a pressure in atmospheres and you want to convert it to torr, then the conversion factor is for every 1 atmosphere, that's equal to 760 torr. So this information is on your formula chart. You can access that. We've linked it up into your Google Classroom, or you probably also got a copy at the beginning of the year. But let's do a couple examples of making pressure conversions. Let's say you have a question that says convert 1.2 atmospheres to the unit torr. Well, like we just said, 1 atmosphere is equal to torr, so you can use dimensional analysis or your train track system, and you put your atmospheres at not horizontal, whatever this is. If you got atmospheres here, you got to have atmospheres down here so that this cancels. And when you do that, you just multiply 1.2 times 760 divided by 1, and you get 912 torr. The last one, convert 458 millimeters mercury to kilopascals. So if you look back to the conversion factors, 760 millimeters mercury is equivalent to 101.3 kPa. So we plug it in like that with our millimeters mercury going diagonal, that's the word I was looking for, to each other so that the units can cancel. And then when you multiply across the top, divide by the bottom, you get 61.0 kilopascals. And I was being aware of my sig figs on this one. So if you guys would try a couple in the Pear Deck slides and then check out the very next video.